Professor Hori's research interests are development of a novel technique towards manipulation of electronic charges and spins based on quantum level in a silicon semiconductor, a silicon transistor. He has various awards and achievements to his credits. Some of them are he is the recipient of 11th JSAP Silicon Technology Division Young Researcher Award. Others, can you please mute yourselves? Others, can you please mute yourselves? Yes. So he's the recipient of various awards. He received the grants in aid for scientific research. He received the 11th JSAP Silicon Technology Division Paper Award. He has a citation of 333 and H index of 9. With this introduction, I request Professor Mahahiro Hori to take over this session. Yes, sir.
Okay. Shall I introduce?
Yeah, you are sharing? You are
Okay.
going to share?
Okay.
Yeah.
So, okay.
Yeah.
First, sorry. This this session has one thema lecturer and two invited lecturer. Thema lecturer has 35 minutes, and for invited lecturer is about 30 minutes. Okay, and first presenter is next slide. Yeah, first presenter is Professor John Kennedy from GNS Science, New Zealand. His research interests are metal and metal oxide non-particle growth and their structure, electrical, optical, and magnetic properties. And then second presenter is Professor Park of Shizuoka University. His research interests are development and application of vacuum for large-scale expression of high-order proteins and so on. And the third presenter is Dr. Barasi of Islam IST. His research interests are surface science, thin film growth, and growth modes at early stage, and so on. Okay, so first presenter is John Kennedy, Professor John Kennedy. Okay.
Thank you, Chair.
Please.
Yes, sir. I've stopped sharing. Yeah.
Okay. I can share my screen now. Okay.
Storage.
Can you see the screen? Can you see the screen now? Hello?
Yes, sir. Yes, sir. You are audible.
Good. Thank you. Thank you, Chair, for a nice introduction. So my name is John Vedamuthu Kennedy. So I'm working as a principal scientist in GNS Science, which is Institute of Geological Nuclear Science, which is the government agency. And I'm also holding a joint position at the principal investigator in Center of Excellence called McDermott Institute for Nanotechnology. I'm also the principal investigator in New Zealand Products Center, where we manage industry-related projects, more about the commercialization side. So today, I'll be talking about defects-mediated high Seebeck coefficient and power factor in transparent thermoelectric thin films. So as you all know, the climate change is a serious issue we need to address. As part of this Paris Intergovernmental Panel on Climate Change, it suggested that the warming is around 1.5 degrees C. So we need to come up with the technologies to mitigate and to reduce carbon dioxide emissions in order to mitigate the climate change. So our group, we have been looking at the low carbon energy. It's probably the crucial way to mitigate the climate change. So our research mostly focused on energy production and use. We're looking at, as you all know, most of the current energy production technologies emits CO2. So we are moving to renewable energy and also same time improving energy efficiency of the systems and process, even appliances. So if all these things contributes small way to reduce the CO2 emissions, then subsequently we can have a better climate in the future. So as you look at it, New Zealand, it's actually in a good position because we are already 90% renewable energy. Being New Zealand is being known for geothermal and water. So our 80% of the energy comes from the hydro and other things are wind and geothermal. We will be 100% renewable in 2025, which is not far away. So we are already 98%. So we're just catching up the 2% as well. So globally, that's an ongoing challenge. And globally, if everyone moves to more renewable energy, then we can reduce the climate change. So one of the ways to contribute for the physical science engineering community is energy harvesting. The fact is, energy harvesting is also a great tool to address the issues climate change and the global warming, because it uses the ambient energy, otherwise it gets wasted. So you all know most of the energy source harvestings are either it's mechanical or thermal energy or solar radiations. You can see that they operate in different frequencies and wavelengths. So energy harvesting is one of the ways where we can save energy and improve efficiency, and reduce the CO2 emission and subsequently contribute to global warming. So there are many methods used in energy harvesting. As some of you familiar, it depends on how it's done. Either it's a photovoltaic or piezoelectric, electromagnetic. Again, as I said, for the physical science and engineering communities, we use our techniques like photoelectric effect and Faraday's law to harvest the energy. So this overview gives you a rough idea of what sort of power density we are talking about, how well the mature the technology is. So today I will be focusing more on thermoelectric, which is primarily works based on the Seebeck effect. And there are some literature available which demonstrated already the power density of even 100 microwatt in a human industrial scale. It's 100 milliwatt. So it's 10 to 15% efficient. It's not as efficient as the other ones, but the key point is we are actually using a waste heat as a source. So that's where the thermoelectric gets more interesting in terms of the low carbon energy systems. And if you look at the globally, thermoelectric, for almost 46% of the current market is most on thermoelectric energy harvesting compared to other systems. So there is a clear demand looking for better thermoelectric materials to have a high efficiency to contribute to the energy harvesting. Thermoelectric is not new. NASA has been using thermoelectric as a way of powering their satellites from almost 40 years ago. And there is various demonstration devices have been done over the years. starting from industrial appliances and even simple sensing side and the automobile industries. So in a thermoelectric heat engines, basically it's simple. When current runs through T junction, it heats up or cools up. So cooling is Peltier effect, depending on the direction of the current flow. When the heat flows through across the junction, the electrical current is generated through the Seebeck effect. So that's the thermoelectric. Then if you look at the thermoelectric generators, which is basically a junction, PN junction in a series mode to increase the operating voltage to spread the heat flow. So it's a simple basic physics used there. So it's not a complicated, but more challenges more on the engineering of these thermoelectric devices. So the other advantage in thermoelectric is there is no moving parts. It's, as I said before, it's a direct energy conversion. There is no pollution. It's sustainable. It's used for self-powering it, and it's a standalone recovery, which is complementary to renewable energy sources. And there is quite a lot of low power applications, like even T-shirts, all those things using a wireless sensor have been demonstrated in the literature. So it is an interesting field, but as a physicist, one would think about why it is, how to improve the efficiency so that it becomes more usable for many applications. As I said, thermoelectric is a direct conversion of temperature difference between to the electric voltage, or vice versa. But what is the key challenge? There is a factor called ZT, which is we call figure of merit, which is direct, which is related to Seebeck coefficient, electrical conductivity, and thermal conductivity at particular temperature. As you see, thermal conductivity is inversely proportional. So you can tune any of these parameters, and normally we call it power factor is the alpha squared sigma, which is called power factor, which is basically Seebeck coefficient electrical conductivity. So there has been tremendous amount of effort put in the past to look at the ways to improve the materials properties. And this review, which came recently using AI and looking at knowledge gap, especially thermoelectric knowledge gap, describing the key materials properties, as well as intrinsic transport and material descriptors, and which is used in the independent, the previous equations of figure of merit. So some of them, they've taken the experimental values, some of them theoretically calculated. So this one is to give you a data-driven approach to predict what sort of material can be used for high efficiency, and also to address some of the challenges in the materials design, because materials design is related to microstructure and scattering, which is a non-equilibrium. You can see that in case of thermal conductivity, you have a lattice thermal conductivity and electronic thermal conductivity, then it goes on to detail mechanism of it. So, but at the end of the day, if you look at the defects plays a bigger role in terms of the electrical conductivity, then if you look at the power factor, which is Seebeck coefficient and electrical conductivity, then you're talking about reducing a Fermi potential and then increasing, tuning the band gap and improving the density of, effective mass. Again, it is related to defects because you're talking about conductivity. So this is actually a nice review, came a couple of years ago, describing overview of what has been researched so far. Even if you look at the history of thermoelectric materials, it's, as I said, the beginning, it is not new. It started in 1950s on the telluride compounds. Then slowly people investigated other magnesium silicate and other compounds. You can see the roadmap is really interesting. And then people are still looking some of the compounds on these materials. So to give you a perspective of the research done over the years in terms of improving figure of merit, you can see people worked on mostly compounds which are improving thermal conductivities, and Hustler came. Currently, we are looking at tin selenium, which has got a higher figure of merit. So it's quite often they're still exploring quite a few materials as well. On the other hand, organic based thermoelectric is starting to come up. You can see in the right hand side slide, they are starting to slowly, they are still below 1, as you can see, but they're starting to come up and improve the some of the properties. So the progress of at room temperature thermoelectrics we are talking about. So the organic material, organic, inorganic, hybrid systems, so they are coming up, and it's interesting to see that because that also can reduce the cost of the thermoelectric materials. So some of the strategies used recent days is to enhance the Seebeck coefficient. Is you can see the diagram A, which gives you a schematic diagram of temperature-induced band conversions. In this case, lead, telluride, selenium. And the B tell you a composition-induced band convergence, where you can see the pseudo cubic structure to tetragonal calcite structure. Then so D gives you a structural transition-induced band conversion. So there's quite a bit of theoretical done looking at the band flattening, band conversion effect. The other one is the energy filtering effect, which is related to effective carrier mass concentrations and impurity scattering as well. So that's the basic physics, which can help us to understand what mechanism driving the material properties. Then there's a good old electron phonon coupling, which is also heavily investigated on systems from amorphous to semi-crystalline and semi-crystalline materials, mostly inorganic and organic hybrid system as well. So the transfer properties are highly anisotropic in these materials, are sensitive to processing conditions and measurement directions. So there is various strategies also used in the lattice thermal conductivities, which is again looking at the grain boundary effects and the dislocation disorders. So this is again highlights how much the defects plays a role in each parameters. So today's my talk will be more focused on the new research happening called transparent thermoelectric. And this is mainly for harvesting energy from smart windows. Imagine you have a glass windows, your sunlight hitting on the glass window, and if we have a thermoelectric coating on it, if we can observe that at the same time this coating is transparent, you can harvest energy. If we are lucky, if we can generate enough voltage, for example, 3 volt, you may be able to even power some of the systems inside the house and inside the building, like bulbs, because you're using a free waste energy as a heat and converting into electricity. So this is the area which is a recent area of interest, and we have been doing quite a lot of work on this transparent thermoelectric materials as a smart windows for energy harvesting. And we do have a project going on last 3 years, which is really promising in terms of the actual product. So if you look at this diagram, which talks about the figure of merit and the band gap, and because if you're talking about transparent, then you need to have a band gap above 3, otherwise you can't transmit the UV light. So very few materials can exhibit high transparency, the same time Seebeck effect, high ZT. So there is a nice material called copper iodide. Then we have done quite a lot of work on aluminum zinc oxide to improve, then indium tin oxide. So I will talk mostly about some of our research on copper iodide, indium tin oxide. So as I said before, you have to please notice that how the charge carrier concentration N is related to alpha and sigma, because that plays a bigger role in a semiconductor. If you are a physicist, you will understand that heavily doped semiconductors, where the metal comes in terms of the carrier concentration and where the semiconductor comes. So you are in between the region where you can have a high power factor, because which can be done by doping. So it's quite good to play around very tiny amount of doping or tiny amount way of tuning the electrical conductivity and Seebeck coefficient. We may be able to have a significant power factor. So this is the area we concentrated more rather than looking at thermal conductivity tuning, which has been done in the past a lot. So this is you can see the right side as a schema diagram, how we envisage this thing to be realized in a few years' time as a smart energy product. So copper iodide, to start with, it's we did quite a lot of, as I said, we are going to present copper iodide and indium tin oxide. So let's take copper iodide. It has got a 3 phases because it's a rock salt crystal structure, and oride structure, and zinc blende structure. So it's a p-type transparent thermoelectric material, band gap of around 3.1. The crystal structure is almost polymeric, as I said before, and it's predicted to be having figure of 0.2 at room temperature and high Seebeck coefficient around 200 microvolt per Kelvin. So it does have a good properties at room temperature, and it has to be in the gamma phase. That's where this, as a zinc blende structure, it can have a high transmission and Seebeck coefficient. So we have been working on making thin films. As I said, the final product we are hoping to see is coating a glass window in your at home or commercial buildings to harvest energy. So we use a technical ion beam sputtering, which is basically essentially you use a small ion source, you hit on the target. In this case is the copper iodide target. Then you sputter them, and then you have a substrate as a catcher, deposit into substrate. So the biggest difference is we use 20 kilo electron volt ion beams. So the sputtered atoms comes with the energy around few hundreds of electron volt, which means your film is atomically bonded to the substrate. So there is no peeling effect. And as you can see, the films are still transparent. So as usual, you look at the stoichiometry of the film. We use a famous Rutherford backscattering spectrometry technique, and the stoichiometry is maintained even if in this case the samples are annealed at in argon 100 degree to 250 degrees C. The stoichiometry did not change much. There's a slight change after annealing. So what is interesting is if you look at the XRD, which is a GA-XRD, the 111 reflection dominates the nanostructured gamma copper iodide. It's originating from the stability energy associated with the growth of crystallites along the 111 direction. So the film growth, the directions, it's basically caused due to the formation of iodine vacancy in defect states. So you can see then Raman also, Raman feature around 125 that was assigned to TO mode. It's also normally associated with the gamma copper iodide. What is interesting more is if we look at the TEM image, we do see some nice metallic clusters. The tiny clusters, as you can, is below less than 10 nanometers. So that's interesting. So these clusters can have influence, but you can see the clusters are distributed uniformly after annealing. So it's and we've done X-ray absorption spectroscopy to look at some of the band edge on these materials, and you can see that after annealing, they become stronger, which indicates that copper zero-like defects increase due to the greater migration from lattice sites. So because you see that you see the pre-edge features on 3D like copper vacancies, so you can easily see the change in the after annealing, which indicates that the defects get improved or increased due to the migration from the lattice side. So we looked at more closely on the electrical properties because that's what matters at the end of the day. As you can see, this is the gives you a nice overview of conductivity and carrier concentrations and mobilities. So you can see the conductivity decreases after annealing. This is a very low temperature annealing. The reason why we operating at low temperature is because that's the maximum temperature you can count from sunlight hitting on the glass window, depending on focus. So we are really keen to be as capacitor to really low temperature to see how we can have a high power factor. So the conductivity decreases due to the hole density from the degrees of copper vacancies. And it's a p-type conductivity because copper vacancies actually play the main source for the holes here. So because of the slight imbalance in the stoichiometry after annealing, you can see that decrease. But the electrical conductivity is also decreased significantly. So it's interesting to see how this thing changing by simply annealing in a low temperature. we did the Sievert coefficient measurements and Hall probe experiments. Again, you can, as I said, it's basically Sievert coefficient, electrical conductivity is related to power factor. You can see there is around 300% increase in around 100-degree annealing. So, which means if the temperature gradient is somewhere between room temperature to 100-degree, you can actually convert them into a voltage. So that's promising on that. So we actually try to explain there's called Pizarro flood, which is basically we call energy filtering, which is plotted based on the assumption of the mass, effective mass is 1.30 times MO. So what you see here is there is something called energy filtering effect. You can see the deviation of Sievert coefficient from the single parabolic Pond model. So energy filtering effect and energy dependent charge carrier scattering at the interface and grain boundaries. And that's what you can see from the band diagram. It nicely explains that there is a sort of energy filtering effect due to the carrier's movement. So obviously, if you look at the optical, it is really transparent from 60 to 80%. And then in fact, it gets better around 100. If you anneal it 100 degrees C, it's already transparent around 70, 80%. So it's really transparent. So you can see through. The band gap is changed to be more around changing from 3.03 to 3.05 EV, which is quite good. So it is really a transparent thermoelectric material. So in summary, we can see the energy filtering effect, which is a key factor for why copper, which explains the copper iron, copper zero like a defect interface along the grain boundaries. So the next material is indium tin oxide, and it's again indium tin oxide is in many applications and flat panel displays and solar cell like that. But here we are looking at more, because it does have high melting point, so we can look at see whether this can be how much Sievert graphite. I mean, figure out merit you can get out of indium tin oxide. So the way we made indium tin oxide is we vary the oxygen concentration in the chamber pressure. Then you can see that we can actually tune nicely the oxygen concentration in the film, which gives us the better controllability in terms of the forming indium tin oxide. So obviously it's you can see the nice structure, and the if you look at more, I mean, reflection, it matches with all the JCDP pattern. But what is more important is if you look at the 440 reflection was only observed at the pressure performed at 4⁻⁶, where we believe the sputtered atoms have more energy than normally film grown at high indium rich metallic clusters. So you can see some sort of cluster formation similar to copper iodide. Then we look at the electrical conductivity. Again, that's what matters in terms of the thermoelectric. So you can see that thin film is deposited at 4⁻⁶ millibar. So the highest electrical conductivity, and also the Sievert coefficient. So normally, as I said, the decrease in conductivity is attributed to the decrease in electron density with increase in operating pressure, because you're filling up the oxygen vacancies. So and also more in the presence of indium clusters also provide some free electrons, which is contributed to the conductivity of the I2O films. Again, this degrees of Sievert coefficient and power factor is likely to be energy dependent scattering, which increase the operating pressure as well. So you can see a nice correlation in terms of the both electrical conductivity and Sievert coefficient. Then we're try to understand the band structure. So we look at again experimentally. We did the XPS, that's synchrotron based XPS, to look at some of the one as indium 3D, indium 4D, and all those peaks. Indium 4D core cell and valence band edge was estimated to be by linear exploration surface peak. You can easily see that valence band shift in the films after the annealing, which which suggested that Fermi level energies, which is due to the reverse Morse Bernstein effect, we call it. So there is a change in the band gap as well. Obviously, great how transparent it is. I mean, indium tin oxide is well known to be transparent, so there's no surprise. So you're working on 80% transmission around 4 nanometer. So which is good. At the same time, we are trying to explain why this you are having a DeFi at the same time is transparent again, you're narrowing the band gap by increasing the operating pressure, which increases puts vacancies, which is we call reverse Morse-Bunsen effect. So that's the kind of another effect happening in terms of the ITO. So many people investigate ITO for many flat panel display, thin film, all those applications, but only very few reports looked at the thermoelectric side. But here the context is more on transparent thermoelectrics, where because it is a transparent material and it is reasonably cost effective as well. And there are many methods you can make tin oxide thin films. It's a lot of low cost methods as well. The key factor here is tuning the conductivity and Seeber coefficient. So oxygen vacancy induced phase separation is the factor which we have a nanocomposite ITO films. Then we can, there is a non-stoichiometric nature depending on the operating pressure you put in the chamber, and also related to indium rich metallic clusters. So the highest Seeber coefficient actually in the non-stoichiometric ITO film, which explains it because it's due to energy filtering, where the interface between indium rich metallic clusters and the ITO. So that's the one contributing to the energy filtering effect. So this is again, it's a really cool to see that we can tune this kind of effects. So we have currently done a prototype of coating 1 meter glass window using a copper iodide. I mean, and with a kind of nanostructured a large surface area. We are actually able to see already 100 milliwatt, milliwatt, which is really amazing. Because so the concept works. We are keen working on to optimize it and put into the product. So this work is done with a strong international partnership from RPI US and NIMS group, and our Boston's group on synchrotrons, and TEM in Melbourne, and also a couple of SRM student university in PTech intensive students contributed to this work as well. With that, thank you for listening.
Thank you, Professor Kennedy. This paper is now open for question. Is there any question or comment? Sorry, I have a short question. Okay.
Yep.
I'm not familiar with your field, sorry, but I want to know how do you obtain the information of defect?
It's basically we're taking care of the looking at the Hall probe measurements and looking at the energy filtering effect. You see, so you know how much vacancies and calculate the effective mass concentration. That's basically what determines the defect.
A defect structure.
Looking at the XRD and X-ray absorption.
XRD. Okay, thank you. Is there any question? Could you comment? Your material is compared to, for example, conventional material. Your material, the merit of your material.
So this is basically the advantage of this material is transparent. So traditional thermoelectrics are not transparent. Like bismuth tellurides, all those telluride materials.
Mm-hmm.
So they have a high figure of merit, but they're not transparent. So here, yeah.
I see. Thank you. Can you see the comment from chat?
I can't see it.
Mm.
Is there any comment there? How will you accommodate transparency in model? Yeah, good.
Yeah.
I can see that. So that's a good question. So in case of copper iodide, the transparency is highly controlled by the way we make the film. So it's purely depending on, we call it sputtering rate, and also surface area of the nanostructured one. So that's highly dependent on the transparency. So in a nutshell, we call it sputtering rate. And that's what we are controlling it.
Okay. Okay. Is there any questions? No. So it's time to finish. Okay. Thank you very much, Professor Kennedy. So next presenter is Professor Park of Shizuoka University. Please.
Professor Park, you are muted. You have to unmute. Professor Park, you are muted. You have to please unmute yourselves. Excuse me, Professor Park, you will have to unmute yourselves.
Professor Park.
Professor Park, you have to unmute yourselves, Professor Park. You can unmute yourselves, Professor Park.
Okay.
Yeah, now you are.
It's okay? Okay.
Yeah,
Okay. Please share your slide.
Okay. Oh, I'm sorry.
Okay.
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 Okay. Thank you, Chairman, for your very kind introduction. And also, I sincerely appreciate the organizing committee and Professor Ikeda for holding ICON 2021. My name is Enoch Park of Research Institute of Green Science Technology at Shizuoka University, Japan. And it's my great pleasure to attend the 6th ICON 2021. Actually, I have visited 2 times SRM, Institute of Science Technology. Unfortunately, this year we can meet you. And however, we can enjoy using in this Zoom system. And my today's talk is application of nano science fused nanotechnology on infectious virus detection. I think this topic is very timely for now COVID-19. And if my presentation is helpful for coronavirus detection, it's my great pleasure also. Okay, just 1 year ago, January 11, only one died. However, 2 months later, 4,500 people died. On May 11 or May 21, 4 million people infected by coronavirus, 250,000 people died. This month, already 100 million people infected and 2 million people died. Why so fast infectious? This is because of very high infectious virus, and also globalized modern globalized society also accelerate the infection of this virus. What we need early diagnostic for surveillance purpose. And when human being became aware of the exist of virus, 1950, electron microscope has been developed. And that time, we can observe virus itself. And after that, serological research is mainstream of virus detection. There are many kind of blotting technology was developed. In 1980, as you know, PCR was developed. All virus sensing was moved to nucleic acid sequence-based amplification method. In 2000, many kind of novel nanomaterial was used for challenge for virus detection. And because of nanomaterial has a very unique properties, for example, optical property, catalytic property, electrical properties. Here, therefore, we think we can synergize this kind of nanomaterial properties. For example, here nanoparticle has plasmonic, magnetic, or fluorescence and catalytic properties. On the other hand, here, carbon nanotube, graphene is all different kind of properties. For example, very highly conductive and also mechanical, very strong. Therefore, if we prepare hybrid nanomaterials, we can enhance the plasma resonance. Also, we can enhance enhance Raman scattering. Also, we can enhance electrical and the mechanical properties. Well, here is some slide, our results. This slide shows the typical application of this kind of nanomaterials. The localized surface plasmon resonance, LSPR, is very famous and very interesting phenomena. We conjugate antibody against the target virus on quantum dot gold nanoparticle. When we mix these two particles with a target virus, this particle was bound on the surface of the target virus. When in here, if two particles located together, located very clear, very close, in that case, we can get very enhanced fluorescent intensity. Here is, we increase the concentration of influenza virus. Shown here, the fluorescent intensity increase depend on virus concentration. We have investigated why fluorescent intensity was depend on the distance of two nanoparticles. To make clear, we control the distance to two nanoparticles using peptide. Also, we control the size of the nanoparticles. We also control the nanoparticle concentration. And after detailing, we optimize this the system. We can find large size cold nanoparticle make strong quenching of quantum dot, but they gradually show the increment of fluorescent intensity with the increment of the nanoparticle size. Therefore, we think it is possible to tune the optimized structure of nanoparticle for most optimized virus detection. And another good example, interesting virus detection system is also very well known surface enhanced Raman scattering. We developed a novel biosensing system based on graphene mediated surface enhanced Raman scattering. A novel molybdenum trioxide nanocube used as a primary source active substrate, and also graphene oxide as a co-substrate. This developed the source-based immunoassay system. We get very high signal amplification, usually almost 1 billion times higher signal amplification. Therefore, we detect this using this system. We detect a clinical norovirus in human fecal samples with limited detection of almost 60, 70 RNA copy per milliliter. However, this kind of a very sensitive system, we need very expensive detection system, also very highly, technical skill. Therefore, what is our challenge? What we want to detect virus on site. We want to do not transfer virus this place to laboratory. We want to detect the virus in this place, at this place. It is impossible to detect virus like pH meta. How to do? In order to detect virus like pH meta, what is the most critical technology? Here is we have many analyte, DNA, RNA, protein, virus, antibody, cells. The most important thing is this electrode can generate signal when this kind of analyte bind on surface this electrode. This is key point. As far as I know, I never hear any practical electrode to detect the virus until now. We developed, recently developed to generate electrical signal when virus bind on surface of this electrode. It's not moving. I'm sorry, it's not moving.
Yeah, Professor, you can stop sharing, close the window, and again open the window and share the screen.
Sharing again?
Yeah, close the PPT, close
Yes.
the PPT. Then now you can open the PPT again.
Okay.
And share your screen
yes.
once again.
Yes. Can you see my slide?
No, it's not visible.
Oh no?
No. You share the screen once again, Professor.
Okay. What?
In the share screen option, you just click on it.
Yes.
Yeah. Now it is visible. Yeah.
Okay. Very sorry. Okay. We developed new system to detect the electrical signal when the virus bound the electrode. Here we use the gold electrode. We coating polyaniline as a conductive nanomaterial, and also we used gold nanoparticle embedded polyaniline, and on the other we prepared NS graphene condom dot, and here the N site was conjugated by antibody against target virus, and here this NSGQD was bound to gold nanoparticle, and this nanocomplex was drop cast on the surface of the surface of the electrode. Here, when in the absence of target virus, we can get very low impedance value. However, here, target virus bound on surface of the electrode, we can get highly increased impedance value. Therefore, we apply this kind of phenomena to virus detection. The synthetic method is very simple. We use the electropolymerization and interfacial layer method, the aniline in organic phase and chloroauric acid in aqueous phase. We synthesize the material and confirm the morphology and the size here. Almost 10 or 12 nanometer size morphology, non-wires morphology. NSGQG it was synthesized by a conventional method. This is the final synthesized NSGQD, and we conjugate antibody on the surface of this N site, and this material was also bind to gold particle embedded polyaniline, and we confirmed the gold particle and the quantum dot in high resolution TEM image. Here, we set up sensing. Here, gold electrode surface was coated by polyaniline, and also our GQD gold particle embedded polyaniline nanocomplex was drop cast on the surface of this electrode. We need 2 more electrode, reference and count electrode. These 3 electrodes used for detection virus. We get a signal from this charge transfer resistance impedance value. First, we have to confirm this electrode really detect that specifically virus or not. We used anti-hepatitis E virus antibody. Therefore, we can detect HEV. Here, we provide many kind of virus. Here, influenza virus, H1N1 and H9N2. Also Zika virus, norovirus-like particle. Here is HEV LP. Here, only we can detect, we can generate signal only HEV LP. However, other virus, influenza, Zika virus, very low impedance. Therefore, we can conclude this electrode is very specific. Also, this fabricated electrode was stuck at 4-degree refrigerator for 1 month to investigate the stability. Here, until 2 or 4 weeks, this performance decreased almost 14%, 10-14%. Therefore, we think 1 week, 1 month, we can use this kind of electrode for detection virus. This is a real virus detection. Using our electrode, really we can detect real virus or not. To detect, we infect the monkey with HEV virus. And every day we collect monkey feces. And one part was used for artificial, the remaining was used for our method to detect virus. This is the result here. And this black circle is from artificial result. And our result is a red square symbol. Our result is shown here, impedance value. And this black circle shows copy number per milliliter. These 2 methods have different dimension. Therefore, we cannot directly compare. However, trend of this curve is very similar. Therefore, we can conclude this method can monitor virus in animal sample. I don't know why, again, stop. I don't know. I'm sorry, again, stop. I'm very sorry, what happened? Okay, next challenge is we detect different kind of virus, white spot syndrome virus, WSSV. This is a very long, this length is 275 nanometer, and width is 120 nanometer size, very big virus. And this virus is causing now very big damage on aquaculture industry, because this virus infect shrimp and causing this black, white spot here, on here usually. Therefore, in this case, almost within 3 to 10 days, almost 100% died. Therefore, it's very big challenge for aquaculture industry to detect this kind of virus. To detect the virus, we need antigen, target antigen. What is antigen here? We investigated this WSV contains almost 60 structural protein, and among them, 35 protein as envelope protein. Among envelope protein, shown here, the most big band, molecular band is VP28 proteins. Very big amount of protein was enveloped in this what happens V virus. Therefore, we target this VP28, and we prepare antibody for VP28 protein. And next, we tried a new electrode, disposable electrode, because we want to detect this virus on site. Therefore, we need disposable electrode, a very cheap one. We used, in this case, we used a very highly conductive silicon rubber as base. And also polyaniline and the cold nanoparticle embedded polyaniline, this nanocomplex was synthesized by as mentioned before, and cast on the surface of this silicon rubber. Here, only silicon rubber, bare silicon rubber, very high impedance value here. However, we coat polyaniline almost half of the impedance value. And we cast GQD also here, very low impedance value. Therefore, we can use this kind of electrode for virus detection. Here, we conjugate anti-VP28 antibody on the surface of this electrode here. And in the absence of WSSV, we observe very low impedance. However, we provide the WSSV bound on surface of this electrode increased very high impedance. Therefore, this electrode is working for detection WSSV. And here, we have to confirm in the linearity of this virus the detection system. We provided 100 copy number per milliliter to 1 billion copy number per milliliter. It's shown here. This impedance value increased depend on the copy number of this WSSV. Based on this result, we make calibration curve here. Very good calibration curve. Correlation factor is a coefficient of 0.999. And using this calibration curve, we calculate limit of detection almost 48.4 DNA copy number per milliliter. Also, this electrode is really selective or not. We check. This is the WSSV target virus. However, other virus, Zika virus, HIV, norovirus, influenza virus, and also serum, human serum, also culture broth, also fecal sample, also some kind of ions, all very similar to control value. Therefore, we can confirm this electrode is very selective and specific to WSSV. And also, we have to check the stability also here. We stuck this electrode for 2 months. Or here, only 1 month, until 1 month, this performance is very similar, less than 10% decrease. Therefore, we think for 1 month, this electrode can be used for detect WSSV. Finally, we have to confirm this disposable electrode can be used real virus detection or not. We use a real sample. WSSV infected shrimp. Here, we get this WSSV infected shrimp and homogenize. We get the supernatant. The supernatant was used for detect by our system and RT-PCR and the Western blot for detect VP28 protein. This is the result. This y-axis indicate RT-PCR result. The x-axis is our result, shown here. Not exactly correlated. However, to some extent, these two methods correlated. At the number of the 1 to 10 is a number of analyte, number of this shrimp. And we have to confirm this virus, detect virus sample contained the VP28 protein or not. Here, the number 1 to 10 is a number of sample, analyzed sample. From 1, 2, 3, 4, here is the 28 band, protein band. However, we cannot confirm here 1, 2, 3, 4 sample. We cannot confirm this band. And also from 5 to 10, we can exactly confirm the very thick with 28 protein band. Therefore, we think from number 510 sample is possible to WSSV infection. And here, number 1 to 4 sample is negative for WSSV infection. Therefore, it's very easily we can detect positive or negative of the WSSV infection in real shrimp. What's the next challenge? We tried to prepare more small size electrode and also more small size detection equipment, and we want to detect the virus on site, not to transfer virus to laboratory. This summary of my talk is we can successfully fabricate the disposable electrode based on silicone rubber, and we can detect the WSV real virus with a high sensitivity, almost 50 DNA copy number per milliliter. This very simple and rapid response and very high sensitive detection method offers huge potential in point of care diagnostics for infectious viruses. It is my last slide. I'd like to appreciate my collaborator, Mr. Takemura and Dr. Ankan, Dr. Sato for providing disposable electrode and electrode fabrication. For Dr. Sato for providing WSV infected shrimp. Also appreciate for collaborating company and also institute, and also thank for participations for medical research and development for supporting this work. Thank you for your kind attention. Thank you very much.
Thank you very much for interesting talk, Professor Park. This paper is now open for question. Is there any question or comment? Sorry, I want to know about the sensitivity.
Yes.
How many number of virus can your system be detected?
In this case, we cannot count the number of virus. We quantified by DNA copy number. Therefore, one copy number is one virus. It's not correct. I don't know exactly.
Okay. Okay, thank you.
Yes, yes.
Is there any questions? Could you read? Can you see the comment in your sorry?
Okay.
Chat.
Okay, chat. How to interpret the change in the impedance device? Okay, I think. Okay, we use the how do we interpret the change in impedance device? Okay, we use the standard sample if we don't have a standard sample, we cannot interpret. Therefore, we prepare known virus sample, known copy number, and we used this known sample, and we have to prepare calibration curve like this. This known value from 100 to 1 billion copy number per milliliter. Therefore, in here, x-axis is known value, and y-axis is our impedance data. Therefore, this impedance data and this known value, we prepare calibration curve. And then next, if we detect impedance, and we calculate the real copy number from this calibration line. Definitely, we need standard virus. Okay, others are too many chat here. I don't. I'm very difficult. Oh, how did you prepare the standard sample? Okay. This also, for example, this WSSV. Dr. Sato is an expert on this WSSV. Therefore, he prepared this WSSV and quantified using artificial and send me. Therefore, I detect the sample. Therefore, I cannot prepare the standard sample. Yes. Okay, did you infect the cell line used for it? Of course, I infect the cell line, partisan cell line, and I used it for detection. It's no problem. However, it's not real sample from on site.
Okay. Is there any questions? No? Okay. So it's time to finish. Okay, thank you very much.
Okay, thank you very much.
Next presenter is Dr. Barasi, please.
Is it full screen now?
Okay, please.
Am I audible?
Okay.
Yeah. So good afternoon, everyone. Today I'm going to talk about all solid thin film batteries, its perspective, issues, and challenges. Before going to the talk, I would like to introduce my group because the data which I'm going to present today is because of them. So we have 5 to 6 PhD students and a postdoctoral fellow, and there are few project students working with me in my group. And these are our group activities. Currently, we have a couple of ongoing projects from DST, SERB, India, and ISRO Respond. So basically, we work on fabrication of cathode, anode, and electrolyte thin films. Also, we work on development of sulfate-based solid electrolytes for all solid batteries. Also, we work on macroelectric multiferroic thin films and nanocomposites. Okay, now let me go into my talk. What is battery? Battery is a device which converts the chemical energy into electricity. Battery consists of 3 components, namely cathode, electrolyte, and anode. Cathode is the one which provides the energy that drives the whole process. For example, in the case of lithium batteries, cathode should have a lithium in it. For example, lithium cobalt oxide. In the case of electrolyte which is a component which allows the lithium ion to shuffle back and forth between the cathode and anode during the charge and discharge. Whereas in the case of anode is a component which allows the lithium to incorporate and deplete depleted during the charge and discharge process. Okay, so batteries can be classified into two categories. One is primary batteries, where the cell reaction is irreversible. So we can use only once. Once it is done, then we have to discard them. For example, the batteries we use in flashlights, etc. Whereas in the case of secondary batteries, cell reaction is reversible. That means we can charge and discharge for several hundred times. Lead acid batteries, lithium batteries, they come under the secondary battery category. So these kind of batteries are used in mobiles, laptops, etc. Okay, so now I'm going to show you how the charge and discharge happens. So the right hand side is a cathode which has the lithium, and you have a liquid electrolyte, and then anode which is typically a graphite which has a graphene layers. So the moment you plug in the battery, the EMF induces the lithium ions to move from cathode via electrolyte, and it will be incorporated into the anode. This is what happens when you charge the battery. Okay, so when we use the battery, that means discharge. When we use mobile or a laptop, what happens? So when we use it during the discharge, electrons flow through the external circuit and we get electricity, and lithium ion comes back to the cathode. So this is what happens when you charge and discharge back and forth. Okay, so this is the band diagram of a complete battery with a liquid electrolyte. Open circuit voltage of a battery is basically decided by the chemical potential of anode and cathode. The way we have to choose the cathode and anode is such a way that, for example, the chemical potential of a cathode should lie just above the highest occupied molecular orbit of a liquid electrolyte. If it lies below, then it will start to oxidize the liquid electrolyte. Same way in the case of anode, chemical potential should lie just below the lowest unoccupied molecular orbital of a liquid electrolyte. Otherwise, it will start to reduce. So the difference between these two chemical potential, mu A minus mu C, which decides the open circuit voltage of a battery. Okay, last year Nobel Prize was given for the lithium batteries to three scientists, namely Professor John Goodenough, Whittingham, and Professor Akira Yoshino. So I will quickly tell their contribution in a couple of minutes. Professor Whittingham was the one who used the reversible lithium ion battery first. He used titanium disulfide as a cathode and lithium metal as an anode. So he used the intercalation chemistry. Intercalation is nothing but the one which I showed in the cartoon just now, like the lithium goes back and forth between the cathode and anode. So he was able to demonstrate the battery with a 2 volt and the energy density of 480 watt hour per kilogram. And then Professor Goodenough's contribution was he has replaced the sulfide based cathode with transient metal oxide based cathode. The advantage of using transient metal oxide based cathode is we can have the higher voltage. This band diagram tells you that left hand side is the band diagram of the sulfide, whereas in the right hand side it's the band diagram of a transient metal based oxide. So we have a higher electrochemical window when we use the transient metal based oxide. Once we increase the voltage, the energy density of a battery can be eventually increased because energy density is equal to voltage times the capacity. So the energy density was increased when we use the transient metal based oxide. And Professor Akira Yoshino's contribution was he used lithium free anode, which is highly safe. So he used carbon based petroleum coke, and he demonstrated the again intercalation chemistry. So this is the contribution from these three scientists. And in 1991, Sony was the first one to commercialize the lithium batteries. Okay, so this band diagram tells you why the transient metal oxide based cathodes are used in the present lithium battery technology. Because of the larger medullum energy, which makes the higher valence state accessible in the oxide. For example, you see here, this cobalt, the highest redox 4+, 3+ is available for the redox process. So with respect to the lithium redox, we have a 4 electron volt energy window. Same way other oxides have a higher electrochemical window. That is the reason these materials are used as a cathode element. So in a battery, there are two kind of charge transfer happens. One is electron transfer, which is related to work function of a material. Another one is the lithium ion transfer, which is determined by the crystal structure and the coordination geometry of the crystal structure. So therefore, it is essential to know the work function as well as the crystal structure of a material when we use them for battery fabrication. Okay, so there are several advantages of lithium batteries. As we all know, like we have been using lithium batteries for mobiles, laptops, etc., because of its high energy density and low self discharge, etc. With present technology, maximum voltage we can go is 4.7 volt with this lithium manganese nickel oxide, and maximum energy density we can get is 150 watt hour per kilogram. Therefore, in order to run a car with this present lithium batteries, we have to use 200 kilogram battery, the battery which weighs 200 kilogram for 250-mile range. And it's been projected that it's been estimated that more than 125 million electric vehicles will be on road by 2030. And early electric vehicles applications, lead acid batteries were used and then zebra batteries were used. At present, again, this tungsten metal oxide based components are used in the present e-vehicle applications. That is called NMC, lithium nickel manganese cobalt oxide. And Tesla is one of the well-known company which use EV manufacturer. They also use the same intercalation chemistry. They replace part of the cobalt with aluminum, and it's called NCA, because cobalt is costly compared to aluminum, and we can have high energy density as well. Okay, so far we have seen the advantages and applications of lithium batteries, but there are some issues with the present technology because of the liquid electrolyte we use. These liquid electrolytes are highly flammable when they are exposed to air. And moreover, if we go beyond 4.2 volt, the dielectric breakdown happens and we cannot enhance the energy density. Therefore, it is essential to replace the highly flammable liquid electrolyte with solid one. So once we replace the liquid with solid electrolyte, then the battery will have all the three components in solid form: cathode, electrolyte, and anode, all three in solid form. So we call that as the all solid battery. So all solid batteries have several advantages. They are highly safe because we don't have any flammable liquid and we don't need any separator, and we can have high energy density. So this left hand side image shows the first thin film battery prepared by Oak Ridge National Group, and this right hand image will tell you how the energy density can be increased. You see here the gravimetric energy density compared to the present lithium battery, you can enhance to more than 300 watt hour per kilogram when we go to thin films because of its low weight. Okay, so now I'll get into what are our interests. We have been working on different materials, like we have been developing cathodes, solid electrolytes, and anode for fabricating all solid film, thin film batteries. So we develop material and we characterize their structural properties, electrochemical properties, also the ionic conductivity properties. So we basically use sputtering, RF sputtering technique to fabricate the thin film batteries. So I will first get into the cathode thin films. We have been working on several materials, but today I'm going to tell like only one or two material in each category. So first I will talk about the lithium nickel manganese cobalt oxide cathode films. So we fabricate these films using sputtering, and yeah, this is the XRD pattern, and this is the Raman spectra of this thin film fabricated at 600 degrees Celsius. So which these two data confirm the formation of this film in a hexagonal layered structure with the space group of R3M. And SEM morphology tells the triangular morphology of these films, and lithium can diffuse through these gaps between these triangles when we do the electrochemical test. And this is the IV or CV curve for this thin film. So this thin film shows a very good electrochemical activity, and its redox peaks are observed at 3.8 and 3.5 volt, which is the fingerprint of this material. Also, we were able to get the capacity in the order of 91 microampere hour per centimeter square at first cycle. So this tells that the films we have fabricated have electrochemical activity. So how we do electrochemical measurement? We use 3 electrode setup. We have a homemade setup. Also, we use coin cell. In 3 electrode, basically you have a working electrode, which is our thin film, and for reference and counter electrode, we use lithium foil. So what we do is we perturb the system using working and reference electrode and measure the response between working and counter electrode. That means apply voltage and measure the current. Okay, so this is the work function mapping of this cathode thin film. We have measured the value to be 5.44 electron volt. This is the measured work function value. As I have discussed in the introduction, work function is very important property to measure because it decides the electron transfer in the material. In addition to the experimental work function value, we have calculated the work function value using the standard hydrogen electrode potential and the lithium redox potential, and the calculated value is very close to the observed value. So how we measure the work function is like we use the parallel plate assembly, where we use a gold as a gold plate. So the potential drop across the film and the gold plate is related to the work function using this formula, and we extract the work function of our thin film. Okay, so now I'll move into the another material again. It's a cathode material, lithium manganese oxide. So so we deposit this film at various temperatures. With increasing the annealing or growth temperature, crystallinity increases, and these films are seen to form in spinel structure. Also, we have measured the optical properties like a band gap of these thin films. As you can see here, the band gap changes with annealing or growth temperature. The change in the band gap can be interpreted, or it can have a contribution, several contributions like a strain induced or quantum confinement effect. Here we have neglected the quantum confinement effect because with increasing annealing temperature, basically particle size grows. So quantum confinement effect is neglected. So we have interpreted this data of changing the band gap and contributed to the strain induced effect. To confirm that, we have carried out the XPS measurement, and this is the XPS spectra of oxygen atom. So the peak centered at 529.7 corresponds to the oxygen atom bonded in a cation, whereas you have a small hump at the little higher energy, which indicates the non-stoichiometric oxidized cations. So when we increase the annealing temperature or growth temperature, so there is always a lithium loss or defects come into the film. So this peak corresponds to the defects. So we can clearly see that the defect peak increases with increasing annealing temperature. So that is how we correlated the change in the band gap in this thing. Again, we measured the work function of this material, the thin film, which is found to be around 5.63 electron volt. Okay, now, I have shown a couple of cathode thin films. Now I will move into the anode material. We work on several anode materials. Now I'll show only one example, which is lithium titanium oxide. Again, we prepare these films using sputtering technique. XRD and Raman confirms the formation of these films in spinel phase with space group of Ft3m, and morphology indicates a very rough surface with dispersed grains. And this is the electrochemical data of these thin films. You see here the CV curve exhibits the redox peak around 1.5 volt, which is the again the fingerprint of this material, which confirms the formation of this film in a right phase. And this is the CV curve measured at 10 different 10 cycles. You can see that the data can be traced one over another. Like that means it's very highly stable material, which exhibits a capacity close to 100 milliampere hour per centimeter square. Again, we measured the work function of this thin film, which is found to be around 5.2 electron volt. In addition to that, from this IV data, we can extract various band edge parameters, which I'm not going to discuss today. So if you go to this paper, you can find how to extract various band edge parameters using the electrochemical IV or CV curve. In addition to that, we were interested to study the lithium ion dynamics when we charge and discharge. In order to study the dynamics of lithium ion, we have carried out the impedance before the redox and after the redox. So this shows the impedance curve of the lithium titanate before the redox, and this is the impedance curve of this thin film after the redox. And we fit these curves using equivalent circuit. You see there are several resistance components and capacitive components, right? These resistive components appear from the resistance of a film, and then resistance associated with the electrolyte, charge transfer resistance, etc. Capacitance generally arise because of the charge accumulation at various interfaces, like interface between cathode and electrolyte, anode and electrolyte, like that. So this impedance data tells us that after the first cycle, the charge transfer resistance increases. You see here, this charge transfer resistance increases. That is because at first cycle, usually the solid electrolyte interface forms, as shown here, small solid electrolyte interface forms, which increases the charge transfer resistance. So using the Warburg coefficient, one can find out the diffusion coefficient of a lithium. So this is the equation where we can calculate the diffusion coefficient of a lithium. These all are the constants, and W is the Warburg coefficient. Warburg coefficient can be extracted from the plot between the impedance, the real part of the impedance, and the omega power minus half. So from the slope, we can find out the value of W, and we can calculate the diffusion coefficient. In this present case, the diffusion coefficient is found to be in the order of 10 power minus 14, which agrees well with the reported value for this material. So now, okay, so far I have discussed about cathode and anode. Now I will show one example for the solid electrolyte thin films we have been doing. So in the case of solid electrolytes, one need to find out how much ionic conductivity it possesses. So how to find out the ionic conductivity? Basically, we do impedance. Just before my talk, Professor Park was talking about a lot of impedance, right? So in an impedance, if you have a resistor and capacitor in parallel, you have a semicircle equation as shown here. Then from this semicircle, where the semicircle touches the x-axis, will give you the DC resistance. From there, we can calculate the resistivity and conductivity. Oh, sorry. I'm sorry, there are some slides missing. Just a moment. So is it visible now?
Yes, sir. Visible, sir.
Yeah. So, okay. So after doing the basic characterization of cathode, anode, and electrolytes, we have fabricated the complete full cell battery. So this is the diagram, schematic of the full cell. We have used NMC as a cathode, lithium lanthanum titanate as an electrolyte, and lithium titanate as an anode. So this XRD clearly tells the presence of all the three layers in our full cell. And this is the cross-sectional TM image of the full cell battery we have fabricated. And you can clearly see the presence of cathode, electrolyte, and then a thin layer of anode at the top. And this is the mapping, EDX mapping of the elements, which confirms the presence of all these elements present in the full cell. So we have fabricated the full cell. Now we have been testing the electrochemical property of this full cell. There are some difficulties in the all solid thin film batteries compared to the conventional battery which has the liquid electrolyte, because in a liquid the diffusion of lithium is very easy. However, here we have a solid, right? For example, you have a cathode here, so the lithium has to diffuse through this electrolyte all the way through this solid, and it has to go to the anode. So that is really challenging one. The lithium diffusion can happen through the vacancy diffusion or interstitial diffusion. So we have been now optimizing the conditions to make this cell work. So yeah, in all solid body, that is the challenge everyone, those who are working in this field, is facing. Like making the lithium to diffuse through the solid electrolyte is a really challenging one, and we have been working on it. Yeah. So and yeah, this is some of the reported thin film batteries. People generally use lithium as anode, which is again it's not safe. So we are actually trying to replace this unsafe lithium with lithium titanate. So here is the summary of my talk. So we have successfully fabricated the cathode thin films and tested their electrochemical properties, and we have successfully grown few of the solid electrolyte thin films and measured its ionic conductivity. Also, we have fabricated anode thin films and characterize its electrochemical properties, and then full thin film battery devices. Yeah, now we are optimizing. Thank you.
Thank you, Doctor. This paper is now open for questions. Is there any questions? So I simply want to know why the thin film battery is safety.
Because we are replacing the liquid with solid. So we are using solid electrolyte. So solid, generally the liquid electrolytes, when we expose it to air, it will catch fire. That is why sometimes we see batteries catching fire, right? So so we can avoid those safety issues when we use solid electrolyte.
Okay. Thank you. Is there any questions or comments? Please see the chat. Sorry, it's no question. Sorry.
Okay.
Is there any questions? Okay, question is in our chat. Please see.
Sorry?
Can you see the chat? Comment from audience.
Okay.
Question.
Thin film battery full cell also prepare glow box. Yes, actually when we use lithium as anode, we need glow box to prepare.
Okay, is there any questions? No? Okay, thank you very much for our interesting talk.
Thank you. Thank you.
Okay. Okay, this session is closed. Okay, thank you very much.
Thank you.
Yeah, on the behalf of the organizing committee, I would like to thank the speakers of today's sessions, that is of this session. The first one being Professor John Kennedy, then Professor Enoch Park, then Dr. Kamala Bharati for their excellent talks. Let me just thank our chairperson of the session, Professor Mashara Hori from Shizuoka University, Japan, for sparing his valuable time and sharing in a very efficient manner. Yes, thank you one and all. So join us for the keynote sessions afterwards. Yes, okay, thank you. Thank you one and all. Thank you.
Thank you very much.